Um, Hello everyone, my name is Gaurav Arora. I am from New Delhi, India, and I am here presenting this ongoing work on testing rank similarity for, I hope it shows up, quantile treatment effects when we reconcile endogenous treatments using propensity score matching. And this paper is part of an ongoing, larger patent project on evaluating the impact of agricultural credit, both formal and informal credit in India, on crop productivity or yields. So this parent paper was presented in last year's meetings, and of course, there's no such study that I'm aware of yet, which evaluates these impacts, especially using field level data. Now, after evaluating the average treatment effect, we wanted to, focus on distribution heterogeneity of impacts. There's a bit of introduction, which, is a step further from exclusive focus on the mean impacts or the average impacts, right? Because it doesn't assume that impact is constant across subjects, and quantile, treatment effects also sort of don't assume that differences in impacts across quantiles offset by transfer. So it sort of is a more sophisticated understanding of the impacts per se. Now, of course, quantile regressions are employed to analyze the impacts heterogeneity, and quantile functions, are by definition nonlinear. And by virtue of this nonlinearity, we have this issue that difference in quantile outcomes, let's say median, difference in median outcomes will not be equal to the quantile of treatment effects, that is, the quantile of the median, median treatment effect, for example, unless we have something called as ranking variance. What is ranking variance? Ranking variance is a subject's relative outcome value, or rank, if it is same across both treatment and control groups. That is, by virtue of treatment, the positioning of the subject in the sample did not change. If that is the case, then we have what is called as ranking variance. I'm going to go over a hypothetical data set, an example to make this point again. So here are these 5 subjects, right? Hypothetically, these are the outcomes without treatment and outcomes with treatment, and this is the difference in potential outcome. Of course, we don't directly observe, we don't only directly observe one piece, right, in data sets. So if I were to look at the average outcome with treatment and reduce on it the average outcome without treatment, I get what is the average, the difference of averages, and this here is the average of differences. Right? And they're exactly equal by virtue of the linearity of the average operator or the expectations operator in the regression framework. In case of quantiles, what happens is that if I look at the same exercise with the median outcome with treatment, median outcome without treatment, the difference is 200, whereas if I were to look at the median of differences, it is 100. All right, so this is an issue that Fargo raised in 2007, and also providing some scientific techniques to deal with such issues, or sort of be able to assume away such rank variance issues when difference in quantile of potential outcomes are not equal to the quantile of different treatment effects. Okay. Why did this happen? Well, it happened because simply by virtue of treatment, a subject that was ranked 4 became ranked 1. This mobility within the sample caused that inequality to happen in the first place. So if we are able to ensure that this mobility doesn't happen, somehow we can statistically test such mobility doesn't happen, then the inequality will hold, and we can really use quantile regressions to get the quantile. Okay. Now, ranking variance is a untestable assumption because we just don't assume, we just don't observe. There's no way to know the rank of the potential outcome for a given subject in So in 2005, it's sort of diluted version. Let's say a statistical dilution was proposed, which is called as rank similarity, and it allows for random variations in subject ranks away from the control. So long as the rank distributions between the treatment and control, subsets remains the same. Okay. Let's see for rank similarity as an entity because joint distribution of potential outcomes is unknown. So where does our paper sit in the literature? Well, one is a purple, at all line of studies, which kind of do not rely on ranking, mathematical, estimation techniques. And if that treatment is endogenous, most studies have been assuming away ranking in papers. Whereas in 2018, a couple of papers proposed tests for rank similarity. Then you reconcile endogenous treatments using ID. Nothing of that sort really exists with propensity score matching, as far as we are aware. And so our paper, short paper, we hope will sit to contribute in that space. If we reject, we can actually go back to propose our proposal, but it's very, very sort of preliminary proposal, but put it out there. Okay. All right. So research objective, we want to propose a method for testing rank similarity when treatment endogenously is resolved by employing the propensity score matching estimator, and we will propose an adaptation, a very simple adaptation of the Kolmogorov-Smirnov distribution test. And we showcase this through a case study, which I talked about earlier. I'm going to quickly talk about this case study. I will not have the time to sort of go over it in a lot of detail. But we employ the PQSAT British dynamic studies in South Asia data set, plot level data set, which are repeated cross sections. And we look at 512 solvent-growing households across 14 semi-arid villages. So these are data sets for collected specifically for semi-arid villages across 5 Indian states. And the data sets range from 2009 to 14. So on one hand, you have a 14-year data set. So, a natural question is why would you evaluate the impact of credit using propensity score? Why not a panel compared to differences in differences structure model, right? Well, it turns out that we're dealing with a data structure that doesn't allow for that. Just because we have 14 years of data set, every household is not going sold every year. It turns out that most of our data set has at max 5 times, a household is going data set in 14. They're putting other things on their plots. Moreover, if I were to think about going towards a quasi-experiment PID approach, I would require at least one pre and post the treatment which is taking credit, but I only have 16% data if I were to do that. Okay, so it's not really possible to exploit the panel structure, even though we look at the data from at the outset, it seems like that's where it should be. So propensity score matching, employing propensity score matching is driven by this data structure. Okay, so and just last thing, that if we were to force a panel structure, it will actually lead to selection bias. It will change the density of yields that we are working with in original sample versus the compared sample that gets us the this particular panel structure EAP list. Okay, so what is our treatment? The treatment is first instance of active access for what is called an agriculturally productive credit. This is defined as a category data set. Agriculturally productive credit refers to loan funds spent for crop production only. We have insufficient contracting to study multiple credit instances. That's why we focus on the first instance. Okay. We do have the credit amounts. We focus on primary definition of yes, no, not the amount per se, because there is a high probability of pre-compliance. Okay. So again, very quickly, a logic model to estimate the propensity scores. We use this vector Z, covariant vector, which is economic status of the household, demographics, and financial institutions. There are some macro variables which we are trying to control for trends in uptake of credit. Okay, of course, these only apply for formal credit. We are also analyzing informal credit with those variables not kind of propensity score. Now, the propensity score is only able to reconcile selection by observables. What about unobservables? So we do a bit of a smart matching, which tries to replicate the differences in time to an alternative differences in space. Right. So I'm not going to go over this technique, but you can read it in the paper. Okay. So we try to sort of propose a quasi-experimental design, which will allow us to identify the causal impact of taking credit on agricultural yields for sorghum in India, India's center villages. Okay. All right. So here is a quantile regression. So this is a quantile function. 25th quantile, 50th quantile, whatever quantile regression on. Here is my parameter of interest. B is the treatment, binary treatment 0, 1. Beta 1 tau hat is my parameter of interest. And then I control for weather, for physical inputs, land quality, some quality of farming operations, skills, variables in the data set, and then also a trend just control for the technological innovations. Okay. Okay, so these are just the results from the previous paper. So here we get our AAEA. It says that for an average household credit, the yields are higher by about 75 kilograms per liter. For a scenario where the mean yields themselves are 300. So there is a pretty strong positive impact of credit that we find. But if you look at the lower quantiles, the impacts are muted. So the impact of credit is all sort of concentrated in higher quantiles of yields. We also further explore risk mechanisms. So where are these? Where is this differential coming from? We look at weather variability. So with higher variability of rainfall and temperature, the impact of credit is muted in those instances, whereas in other, low variability is sort of pulling in already. Similarly, in land size, soil and land ownership, or other mechanisms. And we find a consistent story. But the question is random variance? What about random variance? Are these, can we certainly be sure that these are identified in the sense that are these quantiles of really, right? So we have talked about this. Now I just want to sort of very quickly, I'll take 2 to 3 more minutes as we're done. But in general, I'm working with the output variable, which has a binary treatment, function of a binary treatment, some observables and some observables. And treatment is endogenous, we're acting ESM, okay, and some kind of adapted matching technique, which also tries to cover for unobservables, selection bias. This is condition outcome, quantile function. But what I want to sort of talk about a little bit is this conditional quantile treatment effect for the matching. This is the CQT that the regression estimate is providing. This is the quantile of the mean, when d equals 1 minus the quantile of the mean, when d equals 0, which is the left side of those tables that I was showing you before. Right? So this is difference in quantile of prediction outcomes. The question is whether this is equal to the quantile of the difference. And for that, we come back to our testable implication of rank similarity. Rank similarity implies a conditional distribution of potential ranks, right? So the distribution of ranks are similar across both treatment and control, right? So U of B is equal to the CDF of YD, which is just the yield, And so what we are saying is that the rank distribution conditional on the observables and observables is the same or converges to rank distribution with verbal and observables with and without treatment. The directly testable implication hence will be the CDF on observables equals CDF observables given that we have matched on our matched sample. Okay. All right. So these are the tests for steps for testing what we proposed in the previous slide. So we obtain the set of matched treatment and controlled household pairs. We obtain conditional yields of the regression. We compute empirical CDF of these, right? We directly provide us the distribution of U of P, which is the rank distribution, and then we map the KS distribution test to test whether these are similar across the two states, right? So, an adaptation of the KS distribution test will be given the null hypothesis, the distribution of ranks across treatment and control groups is same. Alternate hypothesis, they are not the same, they are different. It has to be tested jointly across quantums, right? So the KS statistic, this is the basic KS statistic, I don't know. Over it, this is textbook, right? And what we are doing is we are applying it. So here is the CDF yields, conditional yields, due to formal credit access, where treatment is formal credit, treatment is informal credit. Of course, the red ones is the CDF of treated groups. The probability of low yield is lower for treatment treated with access to credit groups, right? But the idea is that these ranks, the more divergent they are, the higher is our propensity to reject. So here we have the test. If I jointly test the null hypothesis across all quantiles, I'm going to definitely reject and similarity. We also did it quantile by quantile. I think that is how our things start. And you see that for the lower quantile here, you might be able to say that if we make our criteria too strong, but otherwise we more or less reject. All right. So that's about it from my end. We just through this paper, which is a part of the paper, want to say that ranks and diversity assumption because of examination for questions pertaining to agricultural risk management, which we don't really see the literature as of yet. What's the next step? How do you sort of now interpret your results? Well, that's work in progress, and the thinking of ad hoc measures, we can sort of look at the dissimilar households which have the dissimilar ranks, which are from the factors with dissimilar ranks, and see where it is coming from. That's more ad hoc, but then there is purpose methodology that we are still sort of evaluating. So that's about it from my end. Questions, comments, concerns, suggestions?
Thank you so much for the nice presentation, and I think it's really good to have the testable implication. And just wonder if you have tried to get the how the test has how large is the coverage or how large is the power of that test, like using the multi-color solutions for?
Yeah, we have not.
Okay,
I'm not. Yeah, just very able to pull this slide to I don't think that.
But it's still nice to have.
It has to have. Yes.
So here you already have those areas. So why don't we just calculate the treatment for each area and then do the sample?
But how would I do it with condition? How would I condition it on the two ways? If it's only
if it's a long so that times treatment each area.
So there are other covariates like X's and there are also so I don't think I can handle these. So I need conditional is the problem. If I could work with the condition, that's the point. That's the point, right? So I want to compare in unconditioned sense, but that's not the only thing. I have to control for the things that affect yields, but can affect itself. Otherwise, it will be confounding. Affect other variables. So that's my sense. Any other questions? Comments? Thank you. Let me cover this next.
Good morning. I'm Kyungin Choi. I'm a PhD student from North Carolina State University. Today, I will present a paper on nonlinear aspects of integration of the U.S. corn market, co-authored by Professor Goodwin. Market integration is an important indicator of market structure, efficiency, and performance. Therefore, many studies have examined the market integration as separated by space, form, and time. And especially in spatial market integration, trade and arbitrage are the keys to linking the market. According to the law of one price, the difference between prices at spatially distinct market should be less than or equal to the transaction cost. Previous studies on spatial market integration have evolved from simple correlation and regression to increasingly flexible nonlinear models. And one of the focuses in this field of study is to examine unobservable friction, such as transaction costs that may affect the spatial market. Most nonlinear models utilize threshold or regime switching models where alternative regimes represent trade or no trade condition. So one condition is given by a profitable trade and the other condition is given by a lack of arbitrage opportunities. In addition, recent studies have considered fully flexible models that allow for nonlinearity without imposing any structure. So for example, Guni et al. And Goodin et al. Applied semi-parametric generalized additive regression model. And in their model, the lack of fixed structures allow them to examine highly nonlinear price linkages. So a conventional threshold model has a richer structure because it assumes constant thresholds, or in other words, constant transaction costs. However, as you know, transaction costs are not static, especially when observed over long periods of time. Also, switching between regimes is triggered by a forcing variable, and many studies have used only a lag price differential as a forcing variable. So we may also consider oil price as a forcing variable as done in our study because it is a major component of the transportation cost and may affect the profitability of spatial trade. So with this being said, in this paper, we propose a novel semi-parametric single index threshold model that includes two key forcing variables. First, we used a lag price differential that is usually used in the paper. And second, we also used the ratio of oil to corn prices. And we applied our model to US principal corn markets using 48 years of monthly price data. So we believe this paper would extend the existing study as we consider nonlinearities in long-run price linkages, such as our period of almost 50 years. Also, our model would allow greater flexibility in the representation of the threshold as we use a single index model and also include the relative oil price as one of two forcing variables. So let me first explain a conventional threshold model. A common specification in special market studies is the following equation 1, where YT is the differential between prices at spatially distinct market. Phi ZT is a transition function indicating switching between regimes, where Z is the forcing variable. And again, normally we use the lag price differential as a forcing variable. In our application, we consider an alternative semi-parametric single index model. We relate the transition between regimes to two forcing variables. Our particular specification is given by equation 2, where DT represents a discrete indicator of alternative regimes. We use two forcing variables, the lag price differential and the ratio of oil to corn prices, and phi is a semi-parametric function. So with the addition of an orthogonal error term, we have specification as equation 3. So we need a normalization for parameter theta, thus we fix the first parameter to be 1, and thus the second parameter need to be interpreted accordingly. So our model is semi-parametric because the exact distribution is not specified and the function phi is estimated using kernels. Okay, so we use Ichimura's semi-parametric least square single index model and choose the parameter vector theta that minimizes equation 4. And since the function phi is not specified, we use kernel where the kernel estimator is as follows. We also need a consistent estimate of the covariance matrix for theta, where V and omega is consistently estimated as follows. Okay, in our application, we use two types of data. First, we use monthly corn prices for the US principal markets. The data covers September 1975 to March 2022, yielding 559 observations. And we consider the pairwise linkages and chose Central Illinois as a central market because it is an important price discovery point. And secondly, we use monthly prices for the WTI crude oil for the same periods. And again, we use the relative oil price as one of two forcing variables. This figure shows the time series plot for the principal US corn markets. And as you can see, the fluctuations were very similar over the years that we observed. And again, we will use Central Illinois as a central market, and we will compare it to other 7 markets. Okay. So before conducting our main analysis, we first conducted a preliminary analysis to see the time series properties. And this table shows the unit root test. So as we can see, all the series are known stationarily at the level and stationarily at first differences. So we confirm that all the series are linked in order 1. We then conducted a Johansen pairwise co-integration test, and we can see a strong long-run relationships in all market pairs. We then conducted a series of linearity tests to see the nonlinear behavior in series, and most of the testing results confirm a nonlinearity in all market pairs. Okay, so this table shows the result for the single index model, and this is our main results. So before interpreting this table, let me first explain this slide. So in our application, we consider 2 regimes, trade and no trade condition. And first, we expect larger price differences would move the system to trade. Therefore, we would expect gamma 1 to be positive if it is not constrained by normalization. Also, we expect fewer price increases would move the system away from trade, in other words, dt equal to 0. And lastly, beta 2 corresponds to the price linkages outside the transaction cost band. And we expect to have the value between -1 and 0 because we expect to see the price adjustment that reduce the price differences. Okay, so as we can see in this table, gamma 2 is the coefficient on relative oil prices, and we can see a negative and statistically significant value in 4 cases, and only in 2 of 3 cases we have positive and statistically significant value. Thus, as expected, higher relative oil prices lower the likelihood of being in trade regimes. Also, R-squared values are very high. So we also confirm the importance of fewer prices as a forcing variable. And in a threshold AI model, beta 1 corresponds to the price linkages within the transaction cost band. And as I explained in the before, beta 2 is the price linkages outside the transaction cost band. And we can see a small negative and statistically significant values in 5 cases. So again, as expected, we can see a price adjustment that reduces the price differentials. Okay, this figure shows the single index transition function, and we can see a rapid and smooth transition between regimes. To summarize our main results and implications of this study, we confirm a strong market integration and the presence of thresholds in the US corn market. The single index model results are consistent with efficiently linked market, though rising fuel prices increase the transaction cost and serve to inhibit spatial trade. Our model would extend the existing study as we introduce an alternative and more flexible model that would better reflect the actual transportation cost. And for a future study, we may also consider other possible factors such as the volatility of corn prices. So thank you for your attention, and I would be happy to get any comments or suggestions.
Why should you use monthly prices instead of daily prices?
We actually was trying to use the daily prices, but for now we just use the monthly, but we are planning to do the daily data as well. So, yeah.
In the case where we got an R-squared one, why is it so high?
You mean here?
Yeah.
Yeah, so that like I think that's why it shows the importance of like the fear prices as a forcing variable. And yeah.
If that's high, is that fundamental study to use for the predictions that
Oh. Hmm. Oh. We. Mm-hmm. We didn't think about it, but yeah. Mhm.
Is there an assumption that trade is only in one direction?
Trade is one direction.
There's two regimes.
Mm-hmm.
Trade and no trade.
Mm-hmm.
But in the threshold situation,
Mm-hmm.
you have trade in two directions.
Mm-hmm.
So there's 3 regimes. So are you assuming?
So it's so our tourism is not about direction. It's about like trade condition and no trade conditions.
Yeah, I think the next step is to look at multiple thresholds. Well, I mean, I think generally you talk about central Illinois, New Orleans, and St. Louis, there is a direction. Certainly, but, this is a first step, I think. We need to look at some different specifications, like looking at, for example, the absolute value. It's not going to be different because that is pretty much a consistent sign from these higher prices that you report.
Yeah.
Oh, thank you. I'll check that out. So hello everyone, this is Kyung-Hoon Ban from Iowa State. I'm a PhD candidate, and this is a joint project with Professor Lance from Iowa State University. And we just wondered if the TOBIT-based model is performing well, and if we are looking for the data set with a bunch of zero consumptions when we estimate the demand system. So let me begin with the motivation. So in order to model the consumer's preferences when we have zero consumptions in the data set, the most famous and most flexible method could be the TOBIT model, which developed by Tobin's 1958 paper, and lots of research were done to extend the TOBIT model, because TOBIT model is essentially an ad hoc model. That means that it's not based on the choice theory, but it's developed for econometrically deal with the zero corner solutions from the observed data set. So these papers are trying to add some theoretical constraint that is consistent with the choice theory. So we do have Wilson Olson's paper and Wells and Lutheran paper that we will get back to later. But on the other hand, because TOBIT models were lacking of those theoretical restrictions, there are another attempts to estimate the corner solutions based on the choice theory. That means they try to derive some estimating conditions from the Kentucky conditions, which is the inherent condition for consumers, or the representative consumers that they use for the cornering out the zero solutions. But this method has that advantage, but this has some disadvantage, because in order to use this Kentucky condition approach, we need to derive the estimating equation from the Kentucky conditions. That means if we have very complicated demand system, it is almost impossible, or it is infeasible to derive those conditions for the estimation. So we saw a clear trade-off between flexibility and theoretical plausibility between the TOBIT-based model and the choice theory-based model. So we wanted to examine the performances of the TOBIT-based model, because TOBIT-based model is really flexible so that it can be applied to almost any kind of demand system, such as QUAs or rank extended models or easy demand system. So we wanted to see how they are performing in terms of capturing the true underlying elasticities. So we designed the Monte Carlo simulation. So for that, we assume the true data generating process as AI demand system, which is one of the most popular demand system used in the empirical works. This is second order flexible, so we are able to test if those TOBIT-based models are able to capture the cross-price elasticities. However, the problem of this AI demand system for Monte Carlo simulation is that this demand system does not have the primary utility function. That means from the standard procedure, we are not able to generate the corner solutions. So we adopted the virtual price approach. So that I'll explain in a while. But in order to apply the virtual price approach, we had to linearize the AI demand system, and we add the additive error terms to the share equation. So here, this is the standard AI demand system equation, and we add the error term for data generation. And this is consistent with the common approaches when it comes to the real data estimation. So how do we use virtual price approach for the data generation if we don't have the primary utility function? So let's consider this constrained utility maximization problem here. Here we have x1 is constrained at a certain level, and the theorem or the proposition of the virtual price is ensuring that there is a vector of positive virtual prices such that this unconstrained maximization problem with that virtual price yield the same exact solution to the constrained maximization problem. So that means as long as we have the Marshallian demand system, which is available from the AI demand system, we can derive the virtual prices that makes the certain zero solutions from that. And we can generate the exact same solution as if we had started from the constrained maximization problem. And it can be shown that this virtual price is unique if the underlying preferences are strictly convex or underlying primary utility function is strictly quasi-concave. So for the estimation side, we consider 3 different Tobit-based models. So first one is the simple equation by equation Tobit. This is the basic model. And when we consider, for example, 3 goods like beef, pork, and rice, this equation, this estimating equation assumes no correlation between 3 consumption demand functions. And we also consider T2 as a system of correlated equation where we consider now we allow the correlation between those 3 consumption Marshallian demand functions. And here we see that using this adding up condition, we ensure the adding up condition for the latent shares, but it has to be noted that this T2 doesn't ensure the adding up condition for the observed shares. That means this model can be used for, actually it has been used for estimation side, but it is impossible to do some simulation or policy intervention simulation using this T2 model if we have the corner solutions in the dataset. And the last one we consider is T3, the Ememiya-Tobin approach, because that T2 does not allow the observed share to sum up to unity or 1. T3 Ememiya-Tobin approach introduced this specific looks complicated mapping structure to ensure that the observed share has also the adding up condition. So these T1, T2, and T3 are nested within each other in terms of the theoretical constraint or choice theory constraints, where we have T3 is the most consistent with the choice theory. And for the setup of the data generation, we consider 3 good cases because this is the simplest case and yet interesting, because if the goods are only 2, then it is obvious to see either both or one good is consumed. So we consider 3 good consumption case for each individual, and 5 individuals makes a single sample. And for each sample, we can calculate 3 income elasticity and 6 price elasticity estimates for each sample at the sample mean. And for the simulation, we have 1,000 replication for each model. That means we have 1,000 set of elasticity estimates for each model. So we need to summarize this one into some single value to compare the performances of all the T1, T2, T3 models. So we consider these 2 criteria,
So one is root mean square error. That is measuring the average distance between the true elasticity and the 1000 elasticity estimates. And the second one is rejection rates. That means we implemented the hypothesis test against the true elasticities. Then we average out the rejection rates across all 1000 simulation replicates. And for the data, we adjusted the parameters so that we have around 40% of corner solutions in the data set based on our research on the actual empirical works from the literature. And we also consider some variation of the setups. Here, for example, for 500 individual setup, we also consider 10% of the corner solution and 40% and 70% of the corner solution, so that how those proportion of the corner solution will affect the performances of the TOBIT models. And likewise, for the middle proportion 40C40 model, we also consider different number of observations to see how the number of observations are affecting the performances of the TOBIT model. And this is the main result of first main result, and this is result of mean root mean square error. So that means the lower the value, the better the performance of each model. And we have 3 lines here: T1, T2, and T3. So overall, you can see that T3 is performing the best among all the TOBIT-based model. That means theoretical restriction actually helps to recovering the true elasticities. And these 2 blocks are for different number of observation and different proportion of the corners. So for example, here we see that all 3 models have some advantages when we have larger number of observations. And second thing is the proportion of the corner solution. And from that figure, we see that if the data set has too many number of corner solutions, then TOBIT-based model isn't a good choice. And the second figure is about the mean rejection rates, and likewise, the lower the better we have here. And the specific interesting thing is that here the T1 and T2 has some problem with higher proportion of the corner solution, but T3 is actually robust to the number of the proportion of the corner solution. But we have to know that this is not implying that T3 is performing performing good, even if there are higher proportion of the corner solution, because we do have some distance between the true elasticity values and the estimates. But here, because they are having relatively low rejection rates, that means that they have low false rejection rates. So these are the key takeaways from our research. So first of all, most importantly, adding theoretical restrictions to TOBIT models is really helpful in capturing the true underlying elasticities. Second one, we also found that having more observations help the performances of TOBIT-based model. And the larger the proportion of the corner solution becomes, the worse the performance. However, we've shown that we've checked that the most restrictive model, the Amemiya-Tobin approach, has lower statistical false rejection rates. And finally, I haven't shown in this slides, but when we use the most restrictive, even if we use the most restrictive T3 model, we have to be careful about interpreting the elasticity values, especially for the income elasticities, because they showed weaker ability in recovering income elasticities than price elasticity. So to conclude, I believe this will be this is helpful in estimating demand system when especially we have corner solutions in the data set. And for the future research, it will be more beneficial to have to find other theoretical restrictions that can be added to this Tobit-based model. Thank you so much. Please ask any questions if you have.
So
Yes.
you try to lead always with math and using
So based on our research, we strongly recommend to use the most restrictive Tobit-based model in terms of capturing elasticities. Of course, we also did the research on capturing the underlying structural parameters as well, but we think that that's not that relevant, because as long as the model is misspecified, that means if the true underlying utility function is, we don't know that, right? And that's probably different from what we are assuming for the empirical work. That means that's not that relevant to our interest, and we, based on our results in terms of capturing the elasticity values, we recommend to use most restrictive form of the Tobit model if we have to use Tobit.
Do you think that these generalized, are these restrictions always true, or just true in your data set?
So that's very good question. So because we also because our true data generating process is assuming AI demand system, so we are actually trying the quadratic utility function as well, then we are getting the same result as well. So we are planning to apply this simulation to a couple of more demand system, and if we are getting the consistent result, I think it is, of course, it is always risky to generalize it, but I think we have some it is we recommend to use the Tobit-based model with the most restrictive one. Does that answer your question, sir?
Well, I'm just trying to think about, we doing a simulation
Yes.
where the restrictions were false. And can you do something like that and get a different answer? I don't know the answer to the question.
Yes, that's correct. And yeah, I think it is important to have that in mind whenever we apply the results. But I believe that to a certain degree, we are going toward the true, or gaining some ability in capturing the true elasticities. Any other questions? Thank you so much. Yeah, thank you so much for the question.
Figure this out here. Okay, let's see. Yeah, bars pissed me off. I think I'm recalling yesterday's session that bar being in the way, but anyway, here we go. Okay, this represents some work here with folks between us, Office of Chief Economist, and folks over at Purdue, including Jason, who's in the room here. And actually, it's a little bit odd that this paper is in this session, because the econometrics come off an archaeological cave painting, but I guess maybe that's the idea. You guys have to tell us what we should be doing. So we were curious. This is purely its interest is sort of policy related. is, as you know, one of the more, I guess this, one of the more significant resiliency impacts in ag due to the COVID back in 2020 was the impact of the COVID outbreaks on packing plants. And when a number of plants slowed down or shut down as employees got infected. So we want to look at that and see if there's a relationship between the shutdowns, the plant size, and if there was a relationship between COVID infection rates in the local community, plant size. And then we look at scenarios on what would be different distributions of plant size and the impacts on the production shocks. And we have a confidential data set. Well, first I'll talk about that in a second. But anyway, there's been some work already done on these issues, on county level relationships between COVID-19 and packing plant locations. Again, it's all aggregate county level. Doing some work came out quite recently, I think it was in food policy by Bina et al., using regional data. But but we really want to get down to looking at the actual plant size level, because from a policy standpoint, there's been interest in perhaps do we support the building of more small plants. If small plants are more resilient, do we support those? So we can do a simulation here and look, at least if you assume that you have a shock that's the same as the last shock we had, what is the impact of having a different size structure on the production shock? And it's a little background here first, just for you who don't, I'm sure most of you probably already know about the production shocks we had. But really starting in early March, like 2020, meatpacking plants, cattle and hogs really had there's some significant production shocks. And plants were forced to either idle or slow down. And there were some major production decreases during that time. But we had a pretty big, the rebound came pretty quick. If you look at the data by mid-June, production is pretty much 90% of capacity. I think I do have some pictures here. And you can see here, the gray line is 2020, it's weekly slaughter. You can see compared to previous years up around like April and May, it's obviously a pretty big dip in weekly slaughter for cattle. And you see something similar here for hogs as well, about the same time. And it picked up pretty rapidly after, but it was pretty significant impact during that time period in the first half of 2020. But you don't see that in broilers. There's a lot more broiler plants. I guess you could say they tend to be smaller, sort of in a distributional sense. If anything, one of the bigger impacts was there was a February freeze in 21, and that resulted in a bit of a drop. I'm not sure what happened over there in 2018 in December. But so you see over here the gray line again this is 2020, and you really don't see any COVID shock there. So this is the aggregate level, the national level data. So what's the story for plants? So we actually have, for agricultural marketing service, we have the plant level data, daily data, and doesn't cover weekends though, but daily data, and it covers the majority of, this data. Companies are required to report to AMS, but it just covers the larger plants, but it does represent the majority of production in the United States. And don't ask me why we don't start before April 6th, but that was just because AMS didn't actually save the data before that. There wasn't any need for the running of the program to save the data. But then I realized, maybe not with COVID, maybe we should retain this data. So that's the breaks we got there. There is other data sets that do start earlier, but they're aggregate, I think either weekly or monthly. But we wanted to look at, it would be interesting to start first looking at daily data. And so we can do a a more detailed analysis and some previous work that's used data off the AMS website and just regional data on the plants. So pretty simple dependent variable here is just looking at underutilization, which you define as sort of essentially a percentage difference between current production and capacity. And the first section, I'm going to aggregate for each plant, aggregate their underutilization over the course of the period, a year, just to make it easier to look at things in a graphical form. Then we do a detailed analysis using data daily for each plant. More negative this is, the more the underutilization is. And I should say that we have, so the variables we have obviously is current production, we have capacity. We also have something called normal production that the plants report whatever they think their normal production is. We did analysis of that. It was a little bit weaker relationships, and for saving time, you don't report that. So this is a regression here, just aggregating each plant over time, which is why you see like 33 plants, 40, 111, because there's 33, for instance, cattle plants in the data set, distinct plants. And take the average over time. You could see that if you look over the course of sort of April 2020 to January 2022, there's no real particular relationship here between plant capacity and underutilization. Also, I want to point out there shouldn't be I should throw in some econometric terms over here. I'm not expecting there's really any endogeneity between plant capacity or dependent variable, because for no plant did plant capacity change over the course of the period analyzed. I mean, they don't, obviously plants are not changing in capacity too often. So but now you look for April and May, you can see quite the negative, statistically significant impact here of plants, larger plants, the larger the production shocks. You see the same thing for hogs, but not for broilers, which and which you would expect. It was maybe not surprising from that in the previous slides I showed you the national data. But I can just show you some pictures here so you can see what's going on here. Now, so these are all the individual plants averaged over the period in the title here, and you're not gonna. It's gonna be pretty hard for you guys to identify the individual plants there. I deleted a few plants, and I did some like jittering over here. And then combined the cattle and hog plants and everything, and its x-axis is presented in a ratio of plant size of total sector. So anyway, try to do some things to maintain confidentiality, but it looks the same if you look at it with the actual data. And you can see here though, so over the full spread of time we had the data for, there's not really any, there's no statistically significant relationship here between plant size and the production and sort of production shocks, underutilization. But certainly things didn't look so good during April to May for cattle and hogs. And you can see larger plants, it's going to be bigger shocks, and it's a pretty similar looking relationship there for cattle and hogs. Broilers, yeah, that's pretty boring over the whole period. Relationship between plant size and underutilization, but right as you expected, right during the height of the COVID, well, it's still there's no real particular relationship. So this is kind of aggregate analysis, but there could be aggregation bias doing it, and so you want to just do a similar analysis, but doing the plant level data. And because we're kind of busy on other things and all that, so far we've only done it for cattle. So very simple equation just set up there is this. By doing it daily, it's much easier to add in other control variables and put in the COVID infection rate, the plant capacity, we have a number of state fixed effects, and various other things like holiday periods, and Defense Production Act as a dummy variable that was instituted in April of 28, and that essentially required the plants to stay open, which is what the plants wanted, and so that you expect that might have an impact. so things like, variables like that, threw in a S&P 500 index just for the hell of it. Let's see. So I won't stay with these too long, but you can see over here, like there certainly is a negative and significant relationship. Plant capacity, simple regression here, just one plant capacity term. Plant age was negative and significant here, so it had some impact on underutilization. It's a very rough measure of plant age that came from separate data. So issues with a lot of your administrative kind of data, it doesn't have too many variables in it, so you have to add stuff. And the second one over here is as you throw in interaction terms, or we have one here, or you break up plant capacity between like pre-June 2020 and after, and you can see that the impact of plant size is still significant negative. It becomes a little bit smaller, and we put in a couple terms or relate the plant capacity before and after, before pre and post June 2020 times the COVID infection rates in the county. So what's kind of interesting here is that it's originally it's negative in April and May essentially, but it's positive, significant after that point. I mean, I should have rescaled this. You can see something besides zeros, but at any rate, it may be suggesting that perhaps large plants were at some point were able to adapt quicker after the initial stage of the outbreaks and impacts. And another econometric one, maybe our previous speaker helped me out there. I did construct by hand the R square for TOBIT. I don't know, was it 1 minus RSS over TSS or whatever, but the values were kind of high. I wasn't sure if I was bleeding it, so I wanted to do more investigation before I put down something that's high, or maybe it has to do with with corner solutions. I don't know, but anyway, it's M. And also what I did over here is I split the regressions across periods just to get some idea of a quick way to see a changing impact over time. And certainly the impact of plant capacity on underutilization is noticeably larger in the April and May 2020 period. It falls after. I did further breakdowns, which I didn't show here to make the table too big, and it goes in. Plant size does become insignificant after about, I think, November of 2020, if you just broke it down that way. You see COVID has the COVID rate in the community has a smaller impact after that. Now there's probably some kind of endogeneity effect between, you expect in some sense, I think between COVID rates in the community and plant size, because plants, these plants are major employers in these communities. So if people are all packed and tight together there and getting COVID, that probably some of that, that probably spread some COVID in the community. But again, that plant size, the plant capacity itself it doesn't change over the period of this study. Oh, and here's a regression. COVID infection rate is a function of cattle plant capacity, and we do see that as you would expect, the larger the plants, the greater the COVID infection rates. At least initially. After that, it became after May 2020, it became insignificant. So perhaps there was some, these plants learned to take measures to control that and did that fairly quickly. See, the R squared drops to something pretty small after 2020. So okay, we have done these regressions, but we're interested, especially in Office of Chief Economists, we're interested in might be some of the policy implications of this analysis. So because one policy, as I mentioned, one policy, something in policy interest might be, well, what if you support the construction of smaller plants that could help reduce maybe just reverse it. It could help increase supply resiliency during future shocks. So I did a couple scenarios here. This first scenario one is kind of a more of a what if. It's not reflecting something actually you think would happen, but this is say like that total daily capacity is unchanged, but maximum plant capacity can't be any larger than a certain a certain like a particular value. So the smaller the plant size, you would need more plants to reach current production. Another one is, well, what if you had the current distribution of plants and you added additional plants above that? That'd be something a bit more realistic, because obviously you're not going to restructure the whole distribution of the industry. And so here's what happens here. This first one over here. So got plant size and the x-axis over here, and the percent increase in production. And here, and the blue line is April to May 2020. So based on April to May regression, one of those early ones I've showed. And the smaller the plant, the more plants you need. But if you add in a bunch of small plants, using small plants, we certainly would have reduced the amount of the production shock in April and June of 2020. But of course, obviously, if you have bigger plants, and the bigger the plant, the less of a production increase you're going to get, because the bigger plants had greater production shocks. And so, that's that blue line is for April and May 2020, and this red line is for April and May of 2021. Things are kind of back to normal. And this one here, you're adding in small plants. Even if you add in like a bunch of small plants, it's really not much of a difference, in production, which you'd expect, because the relationship between plant capacity and the shock essentially became quite small or even insignificant there on. And the other scenario here then, so adding more plants to reach normal production, to say we want to reach and that's again, this is actually a variable that was reported by the plants, what their normal production levels are. And so you can see with the larger the plant, the less plants you need, so you have a bunch of small plants over here. You could, the smallest plant size looked at here was 1,000 head per day, and you could, you would need almost like about 18 plants or so to reach normal production, and that was just for April and May, and you really didn't need much in the way of it. Doing like outside of in a more normal period in April, May of 2021, adding extra plants doesn't really do much to get you back towards normal production levels, because you're already close to there anyway. So what's some of the conclusions here? Well, we found that again that the larger plants tended to have the higher levels of underutilization during the height of that slowdown period. Larger plants tend to be associated with higher COVID infection rates in the county. But there might be some indication that larger plants did also adjust quicker. But so from the simulation here, it's a sort of this leads to decisions, I guess, from society's standpoint. Is you had the smaller plants, you certainly you do decrease your amount of your production shock during the epidemic, but they don't, those smaller plants are not going to they're not going to really have an impact on, I guess you could say, production variability or higher moments during normal periods. So you essentially have a trade-off in increased resiliency during brief periods, and while then you perhaps a trade-off, because then you have you would have more small plants. Small plants tend to be less efficient. So maybe future work would be to look at the trade-offs between plant size and profitability. Future things to think of is if we're looking at sort of resiliency issues across different commodities. For instance, if you're looking at resiliency in meat packing versus resiliency in production of infant formula, is probably you probably want to consider substitution possibilities between between the commodity you're interested in and other commodities, because those probably would play a fairly major, like be a major factor in looking at the trade-offs between resiliency and probably sort of maybe average prices, like a long-term viability of plants, etc. Maybe that's kind of work that's to be done using your Dixon and Pindyke kind of analysis. But this is as far as we've gotten right now. So, any questions? I know it's not much in the way of fancy econometrics. There's no fancy econometrics here.
Question, someone should comment. It would be nice. And maybe you can just say the data before we to do some type of time series analysis to look at dynamics and the speed of recovery from shocks.
Yeah.
And we hear this a lot. I mean, there's so much talk of resilience, and I don't mean to be pedantic, but resilience, by definition, is the ability and speed with which you can recover from a disruption. And I mean, this doesn't get at the speed that these plants recover, and that seems like something that we should take into account in policy, because if there was a disruption and it lasted a week, well, I guess that's not that big a deal.
Yeah. So it'd be interesting to think, what would be like, good approaches to including speed. That's probably, maybe that's something good to add to the current analysis.
Our plants of different size have returned faster or slower to normal production.
I mean, that should be something we should be able to look at in the data. Now we also have data that goes back to the early 90s it covers all plants, but it's either weekly or monthly. I think it's monthly, so you lose some of that excitement of having the daily data. So there's always trade-offs. But we thought you'd start off with the daily data, so you really can capture more of the variability. Yeah, I think that'd be interesting to be able to add some of that, at least look at the speed. Thanks.
I just wonder if the data always
Yeah.
so like would that ownership matter for the
Well, that was actually, I didn't actually check the relationships, but that was one of the fixed effects variables in the model, was like, all the plants under the common ownership. So we had, there were fixed effects for things, for months, for like holidays. Yeah, and plant ownership was like one of them as well. But yeah, we didn't think at the time a particular policy use for that one. So it just was in there as a control variable.
I think that you've done a very convincing job saying that the large plants got hit harder by COVID. You haven't exactly told me why they got hit harder by COVID. And so when I think about policy, that a policy that promoted small plants seems rather radical, heavy-handed, and very inefficient.
Yeah.
And so I wonder if there's some alternative policy that large plants can implement. And so why did they get hit harder by COVID? Was it some policy they got a lot of publicity and so they got hit that way? Did they get more COVID and because they're larger than just?
Yeah, I'm suspecting it's just more, it's more employees on the floor, and that it just results in more spread. There might be some indications they might have recovered faster, or they're able to had more capacity for putting in controls more rapidly.
Spread and they all already had it.
Yeah, that could be it too. Yeah. So, yeah.
So as far as the policy goes, I'm a little skeptical that optimal policy would be to promote small.
Yeah, well, of course, we're not taking any kind of position on plant size policy, yeah. But it's just, point is, it's just, that was purely, that was like a purely like a positive, positive type analysis, so showing, well, if you have this size plants, and, we had let's say we had another shock that was exactly, actually exactly the same as this pandemic. I mean, presumably this wouldn't happen again, because now these plants have learned, and, they probably have, some kind of controls, but of course, you never know what the next shock, what kind of form that's going to have. But,
I would talk that the spread actually happened in like the locker rooms more so than actually on the floor of the plant.
Yeah.
And so there would be ways of staggering people in those, or making those harder, that might be more efficient than promoting small.
But they, I think they probably, they did institute some of those things. I think it's because, it's not like, I don't think, it's probably not like, everybody in the plant got COVID in that May and June. They probably, did institute things to reduce the spend. And in fact, if you look at after that May, after April and May, you don't see strong evidence of those slowdowns or shutdowns anymore. And it's probably more than just the fact that if, I don't think everybody got it all in that concentrated period. It's possible.
I think you're exactly right. So, I have a paper for simulation that incorporates economies of scale. So you have more plants that are more expensive. That's a very different world. And so this is, what we're hoping to do is that these results that go back and redo our model. That right now there's a model that all plants have an equally likely chance of getting hit. So even if it's the case of the bigger plants in the likely to go down, you're right. There's more smaller plants are more expensive.
Yeah.
It means it's going to be worse because you got all the cost of construction. So it's not obvious. You got to do the full cost benefit analysis, I guess.
I just have this bias, I hear all these people promoting small plants. And then I go listen to people like Harold Field and Clem Ward that say people have been promoting small plants for 100 years, and they still don't pay. So,
Exactly. Yeah. Well, yeah. Well, that's the trade-off, right? So, and so that's one issue. Another issue, of course, is more if we look at the society's perspective, you have to say, well, how at least at the consumer level, how vital is it to make sure we don't have major cutbacks for short periods in our meat supply. People might look at that, you might ask the same kind of question for infant formula. How vital is that? What do we,
it's costly to producers too.
yeah, that's the next one, because, we didn't talk about that here, but of course, what happens when when production capacity falls, it means it's going to mean a farm gate price is going to fall. And that's what did happen. The spread between wholesale, meat and the farm gate was, there was that was a pretty big spread that occurred in April and May. It was something similar to what happened with the Holcomb fire back in what was that, 2018, 2019. You got the big spread because suddenly the plant can't process. So at least local hog prices are going to be falling. So so there's issue both at the farm, it has implications for the farm level and for the consumer level, even if the prices are in opposite directions.
Did you say, Joe, that until the farm will fix the fence? Is that right?
Yeah, I said. Maybe that's see, that's probably, that must have been a bad thing.
It's still parameters problem.
Okay.
It's biased,
Yeah. Okay. Well, like I said, yeah. Like I said, this was I have to admit, this was sort of, you kind of like, turning the econometrics to like a little meat press kind of thing over here, and just, everything's in Stata, and go, oh yeah, okay, I'll just change least squares to Tobit. Yeah. Yeah. Okay. That's a good point. So, yeah. Okay. See, that's kind of things right here. Now, one thing we did do, and I didn't do it with the Tobit, but with the least squares, I did try a block bootstrap just to control for the errors, and I think it was keeping, maintaining each, randomly drawing the plants, keeping them with all in the same date, so you don't break the date, because obviously, they're correlated within a particular date, and it wasn't.
That's sort of a
Yeah.
gray area in some of these discussions. What is it standard, three shifts a day, 5 days a week?
Mhm.
Is it overtime on weekends, or what is the capacity?
Yeah, well, this is what they produce, the packers are defining as their daily capacity during weekdays. I don't know why from administrative standpoint, they don't include a Saturday shifts in this data. That's
Well, yeah, I mean,
Okay.
two
Yeah.
shifts can operate, and
Yeah.
they have one shift.
Yeah.
Every night, and,
Yeah.
Their labor's
Yeah.
supply is very sensitive to try and force extra work overtime.
Yeah. Now, there were a few observations, not many, where actually the current production, as submitted by the plant, exceeded the capacity. So, yeah. So, it's not, and I'm not sure USA is necessarily, I mean, I don't know how strict of rules they're providing to these packers at, at how they define things. Yeah. 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 And I guess this data would include some of those, the hog plants would have the high line speeds. I would suspect, given it's all the larger plants. Yeah. I know I should we actually in our other data set, we have I'm pretty sure that the NC State cattle plant is in there. Because we have a lot of the land grant packing plants in there, but university ones, but we figured that's, I mean, from a national perspective, yeah, there you go. But we figured for the national policy perspective that the Purdue packing plant, probably university one, probably wasn't going to have that much of an impact on production. Am I right, or is that a pretty big one there, Jason? Is that like Tyson's? Let's see, we have the chats. There's some people here who had chats that probably, I know there's a couple of these where, it had come up before my presentation, so it's, this was back at 2 o'clock. Sorry, we can't see the slides. We can't see the current slides. Okay, well, yeah, should have opened those earlier, but oops. I'm having trouble going up and down in the chat, but anyway. Any more questions? Any questions for anybody else in this? Any of the other presentations? Oh, I guess we have no more papers, right? We're done. Thanks, everybody.